Let's start with a general overview of MRI. The single steps of an MRI examination can be described quite simply. The patient is placed in a magnet, a radio wave is sent in, the radio wave is turned off, the patient emits a signal, which is received and used for reconstruction of the picture. Let's take a look at these steps in detail. What happens when we put a patient into the magnet of an MR machine? To understand this, it is necessary to at least know some very basic physics, even though this may seem to be boring. As we all know, atoms consist of a nucleus and a shell, which is made up of electrons. In the nucleus, besides other things, there are protons, little particles that have a positive electrical charge, whatever that may actually be. These protons are analogous to little planets. Like the Earth, they are constantly turning or spinning around an axis. Or, as one says, protons possess a spin. The positive electrical charge, being attached to the proton, naturally spins around with it. And what is a moving electrical charge? It is an electrical current. Now, you may remember from your physics at school that an electrical current causes a magnetic force, or magnetic field. So, where there is an electrical current, there is also a magnetic field. Thus, the proton has its own magnetic field and can be seen as a little bar magnet. Let's review what we have learned. A proton has a spin, and thus the electrical charge of the proton also moves. A moving electrical charge is an electrical current, and this is accompanied by a magnetic field. Thus, the proton has its own magnetic field, and it can be seen as a little bar magnet. What happens to the protons when we put them into an external magnetic field? Normally, protons are aligned in a random fashion. This, however, changes when they are exposed to a strong external magnetic field. The protons, being little magnets, align themselves in the external magnetic field like a compass needle in the magnetic field of the Earth. However, there is an important difference. For the compass needle, there is only one way to align itself with the magnetic field. For the protons, however, there are two. The protons may align with their south and north poles in the direction of the external field parallel to it, or they may point in the completely opposite direction, antiparallel. These types of alignment are on different energy levels. To explain this, a man can align himself parallel to the magnetic field of the Earth, in other words, walking on his feet. Or he can align himself anti-parallel, in the opposite direction. Both states are on different energy levels, in other words, need different amounts of energy. Walking on one's feet is undoubtedly less exhausting, takes less energy, than walking on one's hands. Naturally, the preferred state of alignment is the one that needs less energy. So, more protons are on the lower energy level, parallel to the external magnetic field, walking on their feet, so to speak. A smaller number is on the higher energy level, antiparallel, walking on their hands. The difference in number is, however, very small and depends on the strength of the applied magnetic field. To get a rough idea, for about 10 million protons walking on their hands, there are about 10,000,007 walking on their feet. The difference 007 is probably easy to remember, isn't it? Let's take a closer look at these protons. We'll see that the protons do not just lie there, aligned parallel or antiparallel to the magnetic field lines. Instead, they move around in a certain way. This type of movement is called precession. What type of movement is precession? Just imagine a spinning top. When you hit it, it starts to wobble or tumble around. It doesn't, however, fall over. During the precession, the axis of the spinning top circles, forming a cone shape. Protons, in a strong magnetic field, also show this wobbling type of motion, which is called precession. In real life, this is a very fast movement. For reasons we will learn later, it's important to know how fast the protons precess. This speed can be measured as precession frequency. That is, how many times the protons precess per second. This precession frequency is not constant. It depends upon the strength of the magnetic field in which the protons are placed. The stronger the magnetic field, the faster the precession rate and the higher the precession frequency. This is like a violin string. The stronger the force exerted upon the string, the higher its frequency. It is possible and necessary to precisely calculate this frequency. This is done by using an equation called the Larmor Equation. Omega 0 equals gamma B0. Omega 0 is the precession frequency in hertz or megahertz. B0 is the strength of the external magnetic field, which is given in Tesla, T, and gamma is the so-called gyromagnetic ratio. The equation states that the precession frequency becomes higher when the magnetic field strength increases. The exact relationship is determined by the gyromagnetic ratio gamma. This gyromagnetic ratio is different for different materials. For example, the value for protons is 42.5 megahertz per Tesla. It can be compared to an exchange rate, which is different for different currencies. It's now time to take a break. However, let us briefly review what we have learned up to now. Protons have a positive electrical charge which is constantly moving because the protons possess a spin. This moving electrical charge is nothing more than an electrical current, and the latter always induces a magnetic field. So every proton has its own little magnetic field and can thus be seen as a little bar magnet. When we put a patient in the MR magnet, the protons, being little magnets, align with the external magnetic field. They do this in two ways: parallel and antiparallel. The state that needs less energy is preferred, and so there are a few more protons walking on their feet than on their hands. The protons precess along the field lines of the magnetic field, just like a spinning top that precesses along the field lines of the magnetic field of the Earth. The precession frequency can be calculated by the Larmor Equation and is higher in stronger magnetic fields. Why is this precession frequency important? It has something to do with the resonance in magnetic resonance imaging. But to understand this will take a few more minutes. After the break, you should go over this last summary again and then continue. To make communication easier, let's start using a coordinate system like the one used in school. As you can see, the z-axis runs in the direction of the magnetic field lines and thus can represent them. So we can stop drawing the external magnet in all other illustrations. From here on, we will also illustrate the protons as vectors, as little arrows. Maybe you can remember, a vector represents a certain force, by its size, that acts in a certain direction of the arrow. The force that is represented by vectors in our illustrations is the magnetic force. Now, let's look at this illustration. Here we have 9 protons pointing up, precessing parallel to the external magnetic field lines, and 5 protons pointing down, precessing anti-parallel to the external magnetic field. In order to simplify this demonstration, let us stop the animation. What we see in the figure is just a picture taken at a specific point in time. A picture taken just a little later shows the protons in different positions because they precess. The precession actually goes very fast. The precession frequency for hydrogen protons is somewhere around 42 MHz in a magnetic field strength of 1 Tesla. This means that the protons precess around the ice cream cone more than 42 million times per second. Now there are millions and millions of protons in your body precessing this fast. It's easy to imagine that at a certain moment there may be one proton, A in the illustration, pointing in one direction, and another proton, A1, pointing exactly in the opposite direction. The result is very important. The magnetic forces in the opposing directions cancel each other out. Like 2 persons pulling at the opposite ends of a rope. Finally, for every proton pointing down, there is one pointing up, cancelling its magnetic effect. But as we have learned, there are more protons pointing up than down, and the magnetic forces of these protons are not cancelled by others. So we are left, in effect, with some protons, 4 in our example, pointing up. However, not only magnetic forces pointing up and down can cancel or neutralize each other. As the protons that are pointing up precess, there may be one pointing to the right, while another one is pointing to the left. The magnetic force of proton A can be seen as resulting from 2 components. One pointing up along the z-axis, and one in direction of the y-axis. The magnetic force of proton A1 also has a component along the y-axis, but in the opposite direction. Thus, the component of A along the y-axis is cancelled out by A1. The same holds true for other protons. For example, B and B1. For B pointing forwards, there is B1 pointing backwards. they cancel their respective magnetic vectors along the x-axis. In contrast to the magnetic vectors in the xy plane, which cancel each other out, the vectors along the z-axis point in the same direction and thus add up to a new magnetic sum vector pointing up along the external magnetic field. In this direction, the single vectors, the single magnetic forces, add up, like people pulling on the same end of a rope. Now, what does this mean? This means that by placing a patient in the magnet of the MR unit, or in any other strong magnetic field, the patient himself becomes a magnet. In other words, has his own magnetic field. Why? Because the vectors of the protons that do not cancel each other out add up. As this magnetization is longitudinal to the external magnetic field, it's called longitudinal magnetization. This new magnetic vector is important because it is the one that may be used to get a signal. It would be nice if we could measure this magnetization of the patient, but there is a problem. We cannot measure this magnetic force as it is in the same direction, parallel to the external magnetic field. To illustrate this, imagine you are sitting on a boat, floating down a river. You have a water hose in your hand and squirt water into the river. For somebody who is watching you from the shore, it is impossible to tell how much water you pour out. In other words, how much new magnetization is added in the old direction. However, when you point the water hose at the shore, change the direction of the new magnetic field, then the water may be directly picked up and measured by an impartial observer on the shore. What we should learn from this is magnetization longitudinal to the external magnetic field cannot be measured directly. For this, we need a magnetization which is not longitudinal, but transversal to the external magnetic field. Before you walk away, let's just sum up, and when you come back, start with this summary again. Protons have a positive charge and possess a spin. Due to this, they have a magnetic field and can be seen as little bar magnets. When we put them into a strong external magnetic field, they align with it, some parallel, pointing up, some anti-parallel, pointing down. The protons do not just lie there, but precess around the magnetic field lines. And the stronger the magnetic field, the higher the precession frequency, a relationship that is mathematically described in the Larmor Equation. Parallel and anti-parallel protons can cancel each other's forces out. But as there are more parallel protons on the lower energy level, pointing up, we are left with some protons, the magnetic forces of which are not cancelled. All of these protons pointing up add up their forces in the direction of the external magnetic field. And so when we put the patient in the MR magnet, he has his own magnetic field, which is longitudinal to the external field of the MR machine's magnet. Because it is longitudinal, however, it cannot be measured directly. What happens after we put the patient into the magnet? We send in a radio wave. The term radio wave is used to describe an electromagnetic wave that is within the frequency range of the waves which are received by your radio. Well, you can imagine it's not quite like this kind of radio wave. What we actually send into the patient is not a wave of long duration, but a short burst of some electromagnetic wave, which is called a radio frequency or RF pulse. The purpose of this RF pulse is to disturb the protons, which are peacefully precessing in alignment with the external magnetic field. We'll hear about the details later. But not every RF pulse disturbs the alignment of the protons. For this, we need a special RF pulse, one that can exchange energy with the protons. But when can an RF pulse exchange energy with the protons? For this, it must have the same frequency, the same speed as the protons, so to speak. Just imagine that you're driving down a racetrack in your car. And someone in the lane next to you wants to hand you a hamburger. In other words, exchange energy with you. As you are hungry, the hamburger would give you new energy. This energy transfer is possible when both cars have the same speed, move around the racetrack with the same frequency. With differences in speed, frequency, little or no energy transfer is possible. What speed, or better, what frequency, did the protons have? They had their precession frequency, which can be calculated by the Larmor Equation. So the Larmor Equation gives us the necessary frequency of the RF pulse to send in. Only when the RF pulse and the protons have the same frequency can protons pick up some energy from the radio wave, a phenomenon called resonance. This is where the resonance in magnetic resonance comes from. The term resonance can be illustrated by the use of tuning forks. Imagine that you are in a room with different kinds of tuning forks, tuned, for example, to A, E, and D. Somebody enters the room with a tuning fork with an A frequency that was struck to emit sound. Of all the tuning forks in the room, all of a sudden, the other A forks, and only these, pick up energy, start to vibrate, and to emit sound. They show a phenomenon called resonance. What happens to the protons when they are exposed to this RF pulse? Well, just click the RF pulse and see what happens. Remember, some, which were walking on their feet, start walking on their hands. And this has some effect on the patient's magnetization, as we'll see after a closer look. Let's assume that from the net sum of 6 protons pointing up, after the RF pulse is sent in, 2 point down. The result is that these 2 protons cancel out the magnetic forces of the same number of protons that point up. So in effect then, the magnetization in the longitudinal direction, being 6 before the RF pulse, decreases to 2. As we have just learned, some of the protons pick up energy and go from a lower to a higher energy level, thus decreasing magnetization in longitudinal direction. But something else happens. Do you remember what drawings of radio waves look like? They resemble a whip. And what does a whip make the bears do? It makes them walk in line, in step, in sync. They are in phase. Believe it or not, the RF pulse also has a whip-like action, not on bears, but on protons. When the protons randomly point left, right, back, forth, and so on, they also cancel their magnetic forces in these directions. Due to the RF pulse, the protons do not point in random directions anymore, but move in step, in sync. They are in phase. They now point in the same direction at the same time, and thus their magnetic vectors add up in this direction. This results in a magnetic vector pointing to the side to which the precessing protons point, and this is in a transverse direction. This is why it is called transversal magnetization. In summary, the RF pulse causes longitudinal magnetization to decrease and establishes a new transversal magnetization. This newly established magnetic vector naturally does not stand still, but moves in line with the precessing protons and thus with the precessing frequency. The situation can be compared to a ship. Think about the passengers being distributed randomly all over the deck. The ship is then in a normal position. Then have all the passengers walk in equal step around the railing. What happens? The ship leans towards the side where the people are. A new force is established and becomes visible. Let us just repeat. When we put the patient in the MR machine, a magnetic field in the patient, longitudinal to the external field, results. Sending in an RF pulse that has the same frequency as the precessing frequency of the protons causes 2 effects. Some protons pick up energy, start to walk on their hands, and thus decrease the amount of longitudinal magnetization. Depending on the RF pulse, longitudinal magnetization may even totally disappear. And the protons get in sync, start to precess in phase. Their vectors now also add up in a direction transverse to the external magnetic field, and thus a transversal magnetization is established. In summary, the RF pulse causes longitudinal magnetization to decrease and establishes a new transversal magnetization. let's have a look at the newly established transversal magnetization vector. This moves in phase with the precessing protons. The new magnetic vector comes towards you, goes away from you, comes again towards you, and so on. And this is important. The magnetic vector, by constantly moving, constantly changing, induces an electric current. We've talked about the opposite already. The moving electrical charge of the proton, the electric current, induces the proton's magnetic field. This also is true the other way round. A moving magnetic field causes an electric current, for example, in an antenna. And this electric current, induced by the moving magnetic field, is the MRI signal. As the transversal magnetic vector moves around with the precessing protons, it moves with the precession frequency. The resulting MR signal, therefore, also has the precession frequency. But how can we make a picture out of this electric current, which actually is our MR signal? For this, we have to know where in the body the signal came from. How can we know that? The trick is really quite simple. We do not put the patient into a magnetic field which has the same strength all over the section of the patient which we want to examine. Instead, we take a magnetic field which has a different strength at each point of the patient's cross-section. What does this do? We have heard that the precession frequency of a proton depends on the strength of the magnetic field, as the frequency of a violin string depends on the strength with which you pull it. If this strength differs from point to point in the patient, then protons in different places precess with different frequencies. And as they precess with different frequencies, the resulting MR signal from different locations also has a different frequency. And by the frequency, we can assign a signal to a certain location. That's enough about spatial information for now. We'll go into more detail about this in section 33.